Good morning, everyone here in Brisbane, and good afternoon in Hawaii. Can you hear me? Yeah, you can. All right. So today I want to start our journey into representation zeta functions. And so let G be a group. So many nice stories start like that, but our story starts with these numbers. So let me remind you, we defined them yesterday. So we are counting the number of irreducible representations and dimensional representations. So they're irreducible, complex, and we take them up to equivalence. And that's our number R and G. And there are going to be variants to this definition. So if G carries some extra structure, we'll take this structure into account. So say if G is topological, then we count continuous representations. And if G is complex algebraic, then so we are going to map, so it has an algebraic structure, and so we'll count rational representations. So in that case, when G is a complex algebraic group, then this map we can insist that it is polynomial map. Okay? That's a rational representation. And the reason for that will become clear soon. And in cases, so let me put this as a formal definition. So G has a polynomial representation growth if these numbers, they grow polynomially. In N. And in such case, we can define the representation zeta function to be the Dirichlet generating function, which you can cook up from these numbers. So n to the minus s, and goes from 1 to infinity. And if you want, you can also write it down as you go over all the irreducible representations of the group G, which are finite dimensional, and then you take the dimension to the minus s. Right, and so when you take all those with the same dimension, that will exactly give you the Rn, and the dimension will show up here. And that function converges on some right half plane, as we noted yesterday. And alpha G will denote the abscissa of convergence. So alpha G is the abscissa of convergence. So we are thinking about, so this is the function, and we have this alpha here, and that marks the point where to the right of this point, the function converges to an analytic function. Let me already give you an exercise here. So here's an exercise which we are going to use. So suppose that if G1 and G2 are finite or reductive groups, okay, that's something you will define later on in things course, right? then the zeta function of the product of the two groups is equal to the product of the zeta functions. And for the many clever people that are listening to me now, I'm challenging you to find a definition where you can prove this kind of, and taking together these two properties. I mean, this finite groups and reductive groups, they lie in different parts of the universe somehow, but can you find the proof? What is the category of groups? What do you need to say in an abstract way of the group so that you can have this this theorem? Now, I'm looking at this. We will be interested in groups where this sequence is infinite. You have infinitely many Rn's, but this is already interesting for finite groups, and this is so it's Frobenius formula, which I want to write down already now, says the following. So suppose that now that G is finite. So I have only finitely many non-trivial Rn's, right? Because we're looking at complex representations, so there are only finitely many. And so I can still write down the zeta function. Now it converges everywhere. It's an analytic function. But now the values of this function are interesting because they have a geometric interpretation. So let's first do a warm-up exercise. So suppose I have a free group on say M generators, and I'm looking at the collection of homomorphisms from this free group. So this one is free on M generators. And I want to count the number of homomorphisms from the free group to G. Okay, this is a free group. It's generated by M elements. I just need to decide where do I send each of these generators. So this is in bijection with just n copies of G. I just need to choose n elements from G, and I have no constraint. M, thank you. Yeah. Now, let me slightly complicate this. So what happens if I'm now trying to count the number of homomorphisms from, so suppose now that G is a natural number and I'm looking at a Riemann surface closed Riemann surface of genus G, and I want to count the number of homomorphisms from the pi1 of sigma G to G. Now, this group is related to the free group because this group pi1 of sigma G is isomorphic to the free group on two G generators, modulo one relation. And the relation is taking the, say, if F2G is generated by A1, AG up to B1, BG, then we have one relation, A1, B1, the commutator A2, B2, and up to AG, BG. That's the relation, that's the unique relation, and I need to take the normal closure of that, and then I'm taking the quotient. So this is almost a free group, except that I need to solve an equation. So now I want to repeat this. So I can still look at this pi1G as a quotient. I can map each one of these generators into some element of G, except that I need to take care of this relation. It should be trivial. And so it turns out that what you get here, well, you can choose the first 2G minus 1 freely, and then you need to be lucky. You need to you now look at only the sequences that really solve this equation. And it turns out that this is the value of the zeta function of G evaluated at 2G minus 2. Okay, so, and this is an exercise that I wrote on your worksheet, but it's difficult. So you can look at Ser's book. I gave you a reference where you can look at Ser's book. It's still encrypted. So Ser always write very nicely, but also encrypted. So you still have work to do. But it is a very nice exercise in representation theory. Ser uses compact groups. So you, instead of sums, you will see integrals there, but it's just think about compact, finite or compact, whatever you feel comfortable with. So this is the story for kind of a geometric interpretation. So what you see here is that, to say it in fancy words, there's these values of the zeta function, they have interpretation as counting something, as a moduli space of something. And this is just the tip of the iceberg. You can, there's a work of Witten where you need some symplectic measure on, you take a complex Lie group and you use this story, but here you will count only continuous rational representation. So because you're taking complex Lie group, and then again there's interpretation of these values as not as counting something, but as measuring the volume of certain spaces. Okay, which I will not get into that. But this is a big story. Yeah, it's a big story which it's called character varieties, and you can dig in and you can spend many hours, weeks, days, months on that. All right, but my main interest is going to be on zeta functions associated to arithmetic groups. So, our main interest is going to be zeta functions of arithmetic groups. Now, this is also a big zoo. So what is an arithmetic group? I'm not going to define it. The definition, the precise definition of an arithmetic group is very much involved. Again, people spend their whole career studying arithmetic groups. They show up in many areas in mathematics, in dynamics, with relation to number theory, and there's a lot about arithmetic groups. But we can take a definition which covers many kind of most of the arithmetic groups in certain sense. But the extra mileage that one needs to take for the precise definition is, this is a big story. So I won't get into this story, but what I will do, I will just give you the definition of the most common arithmetic groups that everybody uses all the time. So suppose now that I have K is a number field. So that's a finite extension of Q. K could also be a function field, but I will, from time to time, I will go to the function field story, but let's stick to the characteristic 0. So it's a number field. And I'm taking an algebraic group defined over K. Okay, now I need to tell you many things about that, and I won't tell you many things, but I'll tell you some things about that. So in this course, you're looking at linear algebraic groups over algebraically closed fields, and you're thinking about them as varieties, as concrete sets, concrete objects. In that sense, an algebraic group is an answer. But I want to think about, there's another point of view, which is extremely useful is to think about an algebraic group as a question. So think about SLD, for example. So what is SLD? SLD, these are all the elements, all the matrices. All the matrices A, such that the determinant of A is 1. Okay, but let me make it slightly more kind of, so these are all elements x1 up to x1n, xn1, xnn, such that sum of the sign of permutation and then x, we don't need this, but there's a formula, yeah? So what I want to say is that there is a formula. There is a formula, and this formula is defined over z. When you write the determinant, you only use plus and minus 1. No square root of 2, no, nothing fancy, plus and minus 1. So this is defined over z. This is an equation defined over z. And you can solve this equation if you wanted over the complex numbers, or you can look at this and solve it over the real numbers or over the integers, or you can reduce this equation modulo prime p and count the solutions modulo p, or you can choose your favorite ring, consider this equation. Now z is a initial object in the category, so the category of rings. So you can just pick any ring. There's a map from z to any ring, and you can just solve these equations everywhere. So in this sense, an algebraic group is a question, it's not an answer. You can now ask, what are the points of these algebraic groups, and wherever you go. So and to a large extent, if you just take an algebraically closed field, you know completely all the answers. So in a way, the point of view where you're taking the concrete set over the algebraically closed field, it tells you everything you need to know. But you can keep this a more flexible thing, and then you can substitute other rings, and that's what I want to do here. I will do it in various ways, but to begin with, now we can define an algebraic group. So what does it mean now, an algebraic group in that context? So G is a bunch of equations, polynomial equations, and the coefficients are taken from K. And now you can decide which points you want to take. You want to take the K points, you want to take the O points, the integral points, you want to take the points of the algebraic closure, you want to take whatever you want to do, you can do. But you have this, G is now, it's a set of equations, and for any purpose, if you don't feel comfortable with what I just said, you can just, in all my talks, you can think about SLD. Because the problems that we meet here, these are already extremely difficult, and the whole issue is already visible in SLD. So I will stick to the example SLD as much as I can, and from time to time I will jump to algebraic groups, but not in a very kind of serious way. Okay, I was on my way to tell you something about arithmetic groups. So an arithmetic group is so this is going to be G of O, where O is the ring of integers in the field K. And slightly more general, I will look at the S integers. But first, let me give you an example. Again, SLDZ, right? SP2NZI, right? Here's another example. I'm just taking some algebraic group and I'm plugging in a ring of integers in a number field. What could possibly go wrong? Now, OS is the ring of S integers. And what does that mean? It means that I'm taking S is a finite set of places. So these are valuations or norms norms over the field over K. And I'm insisting that this set contains all the Archimedean ones. So we saw yesterday that, well, I mentioned it, that over the rationals, you have the p-adic norms, and you have the real absolute value. So the real absolute value is the one which is not an ultrametric; it's an Archimedean norm, and the rest are all non-Archimedean. They are ultra norm, and that's the case in general. So if you take a general number field, you will see finitely many Archimedean ones, and you'll see the rest will be non-Archimedean. So Archimedean, non-Archimedean is ultra. It's the ultra norm. So you take a finite set of places, and we insist that they contain the Archimedean ones. Okay, Archimedean ones. Let me maybe write down the non-ultra norms. And then OS is going to be all the elements in K, such that the norm of X is at most 1, most 1 for every place not in S. So, example. I'm looking now at Q, and S is going to be the absolute value, which is usually denoted by infinity, because there's a nice story that I don't have time to tell you, but if you ask me, I will tell you. And then P, I'm fixing a prime P. And then what will be Z of S? So I'm going to take all the elements X in Q, all the rational numbers, and I'm going to insist that the absolute value, the norm at say L, where L is different. So I need to take all the elements not in S. So L is different from P, and I need to insist that this is less than 1. So these are all the rational numbers that the denominator does not, can contain only P. Yeah, this is exactly controlling the denominator, if you remember. And so what is this? This is just Z, and I'm inverting P. Okay, and I could do that for any finitely many primes. And I could mix, I could take a ring of integers and then invert primes in the ring of integers. And then I can take these all points, these points for any algebraic group. So for example, so I can now look at groups like SLD and then Z1 over P. Okay, and these are the algebraic groups that I'm going to look at. So this my small correction here is that I'm going to put here S, and I'm going to kind of give you nice color here. These are arithmetic groups for us. Okay, and you can just think about SLDZ. If you're not familiar, if you are not familiar with algebraic group from this point of view, think about SLDZ and keep another example here and keep a third example here, which we'll use at certain points, but that's enough. Just keep these examples in mind. Any questions?
Can you add another prime?
Sorry?
To set S, adding another prime, a cube. What happens?
You can add as many primes as you want, and then you will invert. So what you will have here, you will have instead of P, you will have the product of all primes. You just invert all of them at once. Okay? Sorry?
We're not infinite.
We're not?
infinite is.
Yeah, so this is the reason that we are putting infinite in the non-Archimedean ones is because we can't talk about the ring of integers when it's non-Archimedean, when it's the infinite places. So we only take care of the denominators when these are. Okay. Any questions? Yeah. So if you take the complex numbers, oh, sorry, yeah, repeat the question. So the question was what other Archimedean norms one has. So you can, if you take the complex numbers, for example, you can look at the absolute value, and that will give you a norm. Yeah, and if you have an arbitrary number field, you can embed it in the complex numbers in many ways and compose with the absolute value that will give you different norms, and these are all of them. So since there are only finitely many embeddings of a number field into C, you will have only finitely many non-Archimedean norms, Archimedean norms. More questions from Hawaii? No. Yeah? All good. Okay. All right. So now what I want to do, so now, okay, we have a brief idea what is arithmetic group, and so what I want to do is now look at, so yeah, where are we going to? So what's next? There's a, yeah.
Did you assume that OS is finite?
OS is never finite. So all these things that will always contain the ring of integers of the number field. And this is a number field, so it's infinite, and the ring of integers is infinite. It's a free Z module of rank the dimension of the extension. So so it's always infinite. Yeah, this was the question. Yeah. Oh, S is always finite. Yeah. Yeah. I'm assuming that S is finite. Yeah. Yeah. Okay. The question was if I am assuming that S is finite, and the answer is yes. Okay. So what's next? Maybe some of you read. There's a very nice book by José Saramago. It's called Stone Raft. Beautiful book. And inside the book, so it's about the Iberian Peninsula that disconnects from Europe and starts floating into the ocean. And there are 2 or 3 pages where he says, he spends 2 or 3 pages to explain that sometimes in life there are 2 events that can happen really in the same time, not in a microsecond apart, really in the same time. So he spends 3 pages just explaining. It's beautiful. I don't want, this will be injustice for me to tell you more about that, but you can go and read. So that I was reminded by that book because I'm going to write down now a formula, which is in a way, it's the focal point of the whole series and maybe of the subject. So many things are going to happen in the same time now. Yeah. Okay. So this is the moment. So how do we find representations of arithmetic groups? Yeah. So now so we are looking at the irreducible representations of a group like SLDZ. How do we find this? How do we think about that? Yeah, it's so as you will see, this is extremely difficult, and there's little chance to classify the representation. So this is what it's a discrete group. There's no structure. Finitely generated. So there's a theorem that these groups are finitely generated. So we can look at the zeta function instead of classifying the representations. Maybe we can say something about the asymptotic of the dimensions. So maybe we can say something. So we are looking at representations zeta functions of SLDZ. Yeah, that's our topic here. The main interest. And we want to say something about that. Now, it turns out that there's an Euler product decomposition. So you can have here the zeta function of SLDC times the product over all primes of SLD, zeta function of SLDZP of S. Now, there are many things that are going on here. So let's start to decipher this. So first, as promised, I'm taking SLD, this question SLD, and I'm asking for several answers. I'm looking at points over different rings. Now, this zeta function, since SLDZ has no structure, no extra structure, sorry, rather than a group, we are counting arbitrary representations. Here we are counting rational representations. This is an SLDC. It's a algebraic group over the complex numbers. This ZP is a compact ring, and now therefore we have that this SLDZP is a compact group. Okay, it sits. This one sits as in D by D matrices over ZP, which is compact as a product of compact spaces, and this is a closed subset in a compact space. So this is a compact group. So we are counting continuous representations. Now, why? I mean, I need polynomial representation growth for this to hold. Yeah, so the first thing is does this object exist at all? So spoiler, yes. D is greater or equal to 3, then it converges. And if you're asking why D is greater or equal to 3, the answer is because 3 is greater than 2. So we'll see why this is true. And now, why is this Euler product true? And how are these things relevant here? And if you think about this group here, so SLDZP, this is a profinite group. So this is a propy, well, not propy. This is a profinite group, which I will define soon. It's profinite. In fact, it is a p-adic analytic. And to some extent, I guess Ting will talk about representations a little bit. No? Okay. So those of you who know about representations of Lie algebras, for example, or of algebraic groups, then there's a dimension formula by Weil, and so this is in a way a known story. Everything you need to know about this is there, is available. This is, however, the big mystery in this story. These are the most difficult representations. So we have no choice but understanding what does this profinite and p-adic analytic mean, and we need to understand how do we classify representations of this group. So maybe not classify, how do we think about them? How do we find some of them? How do we enumerate them? So this, in a way, this formula here encapsulates everything that we are going to do. Okay, I need to explain all the ingredients of this formula, and if there are any questions, I'm happy to take them, or I'll move on. Yeah, Lachlan.
In the case where we have a subscript, do we just remove the primes that were...
In the case when we have a subscript, yeah. So the question was if we have a subscript on the ring of integers. So if this was inverting a prime L, then I would remove this prime over here. Okay, and this, so this Euler product decomposition, this is a theorem by Larsen and Lubotsky. I will talk about the theorem, I will talk about the conditions, so when does it hold, and all that, that's coming. But already now, I want to tell you, why are these groups relevant at all? So I'm now, it's the first stage, I'm not going to tell you why there's an Euler product decomposition, but I want to tell you why are these groups relevant to the story. So, so that would be kind of the.
Maybe Q makes more sense than
Q? Why? So the question was.
Everything is said.
You mean here?
Yeah.
So the question was, why do I put here C? You will see why. You will see why. And there's a question, can we replace SLD by G of Z for G any Lie group of real rank greater than 1? Yeah, so I'll say all so I promise to answer this question, but I don't want to do it now. But can this question come up later? Okay. Once I say enough things so that this question will make sense for all of us, please ask it again. So why are these groups relevant at all? So here is say SLDZ. And now SLDZ sits in SLDZP. And Z is dense in ZP. Right? Remember, this was one of the definitions was this is the completion, so it's dense. Now, it turns out that SLDZ is also dense here in SLDZP. So this is a dense embedding. And now suppose somebody tells me how to, or somebody gives me a continuous, irreducible representation rho into some GLNC. So remember, we are looking, we are trying to get representations of SLDZ. But if somebody gave me a continuous irreducible representation of SLDZP, then I can compose it with this dense embedding. And this composition, well, firstly, this is a representation, it's a composition of homomorphism, that's good. But the next thing is that this is still irreducible. And the reason is because of this dense embedding. So if there was an invariant subspace for this group, there was invariant subspace, proper subspace for this group, because it's dense, I can approximate things. So if somebody told me how to construct representation of SLDZP, I can manufacture a representation of SLDZ. So that's the relevance of this thing here for all primes. But I can also embed this inside SLDC. And now I can take a rational representation into some GLNC. Now, Z is not dense in C, but it is Zariski dense. That is to say, if you have a polynomial that vanishes over all, let's start with Z, yeah? Take a polynomial that vanishes over a complex polynomial that vanishes over all the integral points. That's the zero polynomial. It must vanishes over C. And similarly here, if you have a polynomial that vanishes over SLDZ, it will vanish over SLDC. That's the meaning of Zariski dense. And so the same story here, if I have a rational representation, then that's an algebraic representation. And so I can compose this with the embedding, and I can pull it back. So I have now a map from here to here, and that will give me an irreducible representation of SLDZ because this is dense here. Yeah, rational irreducible. Thank you. Okay, so that's the relevance of this SLDC to the story. Okay, there's some of the representations of SLDZ are coming from representations of SLDC. That's for sure. In fact, yeah. So and all of them, right? So I can import all these representations of SLDC. I can import them and pull them back to SLDZ. Similarly, I can do this for all the primes for all the SLDZP, and that's a big collection of irreducible representations. And the mystery that we will try to understand why are these organized in a way that I can write down an Euler product decomposition in this way under certain conditions. Yeah, there's conditions here. Okay, so that was my motivation to drag you into periodic analytic groups and Profinet groups. And I really hope that you did your homework about ZP, because that's going to be, I'm going to rely on that I will prove very little, but I will build on your intuition that from the story over ZP. Because in a way, not much changes, except that things are becoming non-commutative now. Okay, it's a lot, but that's in a way, in certain aspects, this is just that. All right, so now I want to move to talk about profinite, Propi, and periodic analytic groups. So just a quick reminder, it's called reminder 1, that G is topological group. It means that there are two maps, mu from G cross G to G, that's the multiplication, and the inversion. So these are both continuous. That makes a G a topological group, and G is locally compact. Say Hausdorff. Locally compact. If it's Hausdorff and there's a exist for every point in G, there exists a compact. Okay, that's a group, right? So whatever happens, the identity happens everywhere, but there exists say a compact neighborhood. So real numbers are locally compact. QP is locally compact because ZP. So, for example, the real numbers QP, SLDR, SLDQP. These are all locally compact, and the gist of these groups, the gist of what you get from this local compactness is quite remarkable, because you have a How measure. So there's a theorem that there's a How measure, which is the analog of the Lebesgue measure. And here you need to distinguish between left and right because things are not commutative. So say a left How measure. So this is a measure on G such that the measure of a set of a translation is the same of the measure of the set for all measurable sets. So for all G in G and all E measurable. So you can import your intuition from Lebesgue theory if you haven't seen locally abstract. This is called abstract harmonic analysis. When you deal with abstract locally compact groups. But you can import your intuition from the real numbers and Lebesgue measure, because the Lebesgue measure is exactly the Haar measure in the case of the real numbers and addition. So you can import your intuition from there, except we should be careful because things are non-commutative. So that's one reminder. The second one is that among all locally compact groups, there is special family which is called the Profinet Groups, and that's for that I want to remind you. I need one more thing. So so suppose I is a directed set, then this is something we touched before, but I need it in a slightly more general form now. So this is a partially ordered set where for every I and j, there exists a k such that k is greater or equal from I and j. Okay, so it's a partially ordered set where I can always find an element which is larger than any two. And now suppose I have GI, collection of groups, rings, sets, whatever you want. So there's a collection of these, and they are organized in an inverse system. And then what does that mean? It means that there are maps phi ij that go from G j to Gi whenever I is greater or equal the other way. No, whenever j is greater or equal to I. So, of course, there are many ways to do this, and every book, well, the books will be divided into two equivalence classes of left and right. So here I'm just, with the notation that I will use is that you have the greater index j, and the map will go from j to I, and that j will stand here. So I'm thinking about the map going from gj to gi. It's always that convention. So what does it mean that this is a directed system? And yeah, I won't have time to tell you much more about that, but I will just finish the definition and give you a few examples. What we want is that whenever I is less or equal to j, less or equal to k, it makes sense to compose phi k j with phi ji, and that should be equal to phi ki. That's one thing that we need, and the other one is that all the phi i's are the identity maps. Okay, so that's a directed inverse system, and with the inverse system we can form the inverse limit. Yeah, I know. Yeah, thanks. Masood said 2 minutes. So I'm looking at all the collection of elements Gi, such that phi ij of quick quiz. Should I put here J or Gi? Gj, right? The larger one. Gj, and that should be equal to Gi. Okay, so these are compatible systems for all I less or equal to j, and that's a subset. Even well, let's to begin with subset, depending now what you want the Gi's to be of the product for all I, and the reason we spend so much time about on the periodic integers and all these points of view is because now you are experts and you know that in the example of the periodic integers we have the product of z modulo p to the I z, and that's exactly in the limit z modulo p to the I z. That's the inverse limit that we saw yesterday, except now our set doesn't need to be linearly. So what's so special about here? Well, first, these are finite, commutative, and linearly ordered. Like there's a linear order, and that all we get rid of that. So we allow directed sets in general, and we, for the moment, we'll soon come to the finiteness, because a profinite group will be exactly the inverse limit of finite group. Okay, a pro anything is the inverse limit of that anything. Okay, so we are going to have profinite groups if all these groups are finite groups. And so for the periodic integers, this is an example of a profinite group. Even a pro p group, it's the inverse limit of finite p groups. Okay, and all these will come up tomorrow. I will leave a slightly expanded version of what I said today with some exercises and some hints of where we are going. Thank you all. Thanks to the corrections to the typos that I have on my exercises. I will. You can, if you look at the exercises, you can just solve whatever you find suitable. And some exercises we look to you unrelated to what we've done so far, but you have the tools to solve them. I'm encouraging you to solve them because at some point I will say, look, I'm taking this exercise and I'm throwing this into the game. And if you have done it, you'll be completely in the game. All right, that's all for today. Thank you.
Hi, Uli, this is Brechtje.
Hey, Jorge.
Hi. We have our problem session right now. So are you going to post the exercises right away, or?
Sorry, can you say it again?
Could you post the exercises right away, because our problem session starts now?
I already put it last night. So on the representation zeta functions section in Slack, there is it's called pin documents, or and well, you will see the latest version of the exercises.
Okay, so you're updating it. Okay.
It should be updated. If you see something from last night or from this morning, then it means that it's updated. The way to know is if you see that the last exercise is asking you about log and exponent in a non-commuting environment. Power series in a non-commutative environment.
Okay, thank you.